Okay, guys. The next speaker is Professor Chen Zhijie from Tsinghua University. The title is Mean Field Equations and Green Functions on Torus and Lim Equations. Let's welcome.
Thanks for the introduction and thanks the organizers for the invitation. It is my great honor to give a talk here. So today I will talk about three objects: mean field equations and green functions on torus and the Lamé equations. So we consider a flat torus in the plane generated by vector 1 and vector tau. So this is we call the mean field equation on the torus. The left-hand side is very simple. The right-hand side, there is a Dirac measure at 0 and with the parameter a pi times an integer n. So this is a mean field equation. And we also consider the green function on the torus. So the green function is a unique solution of this equation. This green function, we mean the green function with singularity at the zero. So from this green function, we can define one variable green function. We call it multiple green function Gn with n variables. So divided by the green function G. The third object is the integral Lamé equation. This is a second order linear complex valued ODE. So here the potential here is a Weierstrass P function, and here is the integer n times n plus 1, and is a complex parameter B. So today in this talk we'll talk about these three objects. So these three objects are related to each other in a very essential way. So let's recall for the n variable green function Gn, we say this Z is a critical point if the derivative with respect to every Zi is equal 0. And since the green function G, this green function is an even function. So you can see that if this is a critical point, then minus Z1 minus Z is also a critical point. So these two critical points may be the same in the torus. If they are the same, we call the trivial critical point. And if they are don't the same, we call the non-trivial critical point. So non-trivial critical point must appear in pairs. So the starting point of this talk is this theory proved by Zhijie Wang in 2015. They say that these three statements are equivalent. So the mean field equation has solution is equivalent to the multiple green function. Gn has non-trivial critical points, and it also equivalent to that exists B such that all monogeometric matrices of the Lamé equation are unitary matrices. So these three statements are all equivalent. So from this theory, there are many cross applications between these three objects. So in this talk, I will introduce several results from this point, from this viewpoint. So our motivation is the general mean field equation on a compound Riemann surface. And the right-hand side that you can have many Dirac measures. And this equation arises from statistical physics as an equation for the mean field limit of the Euler flow. So this equation called mean field equation. So this equation has been very widely studied in the literature by it is a hot topic in EDPDE. So to prove this equation, to see this equation whether has solution or not, we want to know when the solution will blow up. So suppose there is a set called critical parameters. So you fix the alpha j are fixed, and that here is a parameter rho. So you want to know for what low this equation has a priori estimates. So here is the set of critical parameters defined in this way. So Bartolucci and Tarantello, they considered the blow up of this equation. Suppose UN is a sequence of solutions with low n and low n converge to low infinity, such that this solution sequence blow up. Then the nonlinear term, this term will converge to a finite sum of Dirac measures. Dirac measure. Here the coefficient beta I, if the blow up point xi is not the singularity, q. This equation have a singularity at qj. So if the blow up point is not as a singularity of the equation, then the beta I is always a pi. But if the blow up point xi is equal some qj, then the beta I equal a pi times 1 plus alpha j. Alpha j is this coefficient. So in particular, the limit of the low n is sum of beta I, so belong to this critical parameter set. Critical parameter set. So in other words, as long as low is not in this critical parameter set, then solution sequence cannot blow up. So as long as you low is away from the critical parameter set, then all solutions are uniformly bounded from above. So you have the a priori estimates. Once you have the a priori estimates, then the Levi-Shorter degree is well defined. So Chen Jingquan and Chang Shoulin, they compute the Levi-Shorter degree and has a following sequence, has a following consequence. So for simplicity, we assume alpha j all alpha j all integer. Alpha j all integer, then this set is just a pi times an integer. Any element in this critical parameter set is just a pi times an integer. So this set is just a pi m. So then, as long as low is not a pi times an integer, then they can prove the and assume the genus of the Riemann surface is positive. Then they can prove the Levi-Shorter degree is always positive. So in other words, then the mean field equation always has solutions as long as this low is not a pi times n, a pi times integer. The Levi-Shorter degree is always positive. Before the degree counting formula, the variational method also works, but only for small non-critical parameters such as low less than 16 pi, and also for the critical parameter low equal a pi, but needs under some further conditions on the Riemann surface. Even to now, the critical case low is a pi times the integer still remains largely open. So to deal with the critical case, now we focus on the case that the Riemann surface now is a torus. So let's consider this simple looking equation. Now we consider the Riemann surface a torus, and we consider that the only a Dirac measure at 0, and here is the parameter low. So in geometry, a solution U of this equation give a metric with constant Gaussian curvature 1, but has a conic singularity as 0. So this equation also arises from conformal geometry. So we apply the previous result to this simple looking equation. The result says that if low is not a pi times n, then this equation always have solutions. So the remaining case is low is a pi times n. And this case was first studied by C.S. Lin and Jinlong Wang. They proved that then whether this equation have solutions or not depends on the geometry of the flat torus. That is, depends on the choice of the vector tau. Vector tau. So here we denote omega 0 is 0 and omega 1, 2, 3. This is a basic 3 periods. Since the Green function is an even function, so you know that the 3 half period omega k over 2 are always critical point of the Green function. So the Green function always has 3 trivial critical points. So a basic problem is then how many critical points does the Green function have? Or equivalent, how many non-trivial critical points does this Green function have? This is the basic problem. Lin and Wang, they prove that this mean field equation, the right-hand side is A pi times 1. This is the first critical case. They prove that this equation has solutions if and only if the Green function on the torus has non-trivial critical points. This is if and only if. Then they can prove that the Green function on the torus has at most 1 pair of non-trivial critical points. That is, the Green function either has 3 critical points or 5 critical points. 5 critical points. This is the main result of this paper. Here are 2 examples. For example, when tau is purely imaginary, that is the torus is a rectangular torus, then the Green function has no non-trivial critical points. So this equation have no solution. But if the real part of tau is 1 over 2, then that is the torus is a Rambert torus, then the situation is complicated. Then there exists B0 and B1 such that when the imaginary part of tau B smaller than B0 or bigger than B1, then the Green function has a pair of non-trivial critical points. This is if and only if. For example, for this special case, they can know the non-trivial critical point is these 2 points. These 2 points. So in conclusion, this solution, this equation have solution or not depends on the choice of the torus. Depends on. They proved this theory by showing that there is a 1-to-1 correspondence between pairs of the non-trivial critical point of the Green function and even solution of this equation. Then they proved that for this equation, if this equation have a solution, then it has a 1-parameter scaling family of solution U beta. Beta is arbitrary. And furthermore, among this 1-parameter family of solutions, there is a unique one is even, and all other are not even. And when let beta tends to infinity, then this sequence of solution will blow up, and the blow up point will give a non-trivial critical point of the Green function. Non-trivial. So this is a connection between this equation and the Green function. Then they prove that this equation has at most 1 even solution by BDE methods. So these 2 results together implies the Green function has at most 1 pair of non-trivial critical points at most. Sorry, this is a typo. So they cannot, they don't. So the method of proving the Green function has at most 5 critical points is indirect. They use the PDE. They prove the PDE has at most 1 even solution to imply the result for the Green function. And later, Elemengo and his cooperator give a direct proof of this result for the Green function from using anti-holomorphic dynamics. So what you can say about the non-trivial critical point? Lin and Wang, they proved that if the non-trivial critical point exists, then these non-trivial key points are minimal points of the green function. And then all the three trivial critical points are non-degenerate center points. That is, the Hessian is less than 0. So once you have 5 critical points, then the non-trivial critical points are minimal points, and the other 3 trivial critical points are non-degenerate center points. So you may this non-trivial critical points are minimum points. You may ask whether they are also non-degenerate. This is a difficult problem. So recently, joined Fu and Lin, we can prove this the non-degeneracy of this non-trivial critical point. So we can prove that these non-trivial critical points are also non-degenerate. So in other words, once the green function has 5 critical points, then all the 5 critical points are non-degenerate. So this is our recent result. For the general case, you want to see whether when low equals this number, whether this equation have solutions or not, then it is natural to consider let low converge to this number and to see whether the solution sequence blow up or not. If the solution sequence does not blow up, then you obtain a solution at this parameter. So you consider let UK be a sequence of this solution of this equation, and we suppose the solution sequence blow up. Then Zhijie Wang proves that if low k is not a pi times n, then the blow up set gives a trivial critical point of the multiple green function Gn. If low k equal a pi times n, then the blow up set gives a non-trivial critical point of Gn. And based on this result, they can prove that for general n, this equation have solutions if and only if Gn has non-trivial critical point. Non-trivial critical point. So from this theory, we also ask, so how many critical points does Gn have? And is the critical point of the Gn is non-degenerate or not? So we want to consider these 2 fundamental questions. So in particular, the non-degeneracy of critical points have many important applications in elite PDE. For example, in constructing solutions via reduction method and proving the local uniqueness of bubbling solutions. To apply these 2 methods, we usually need some conditions like the non-degeneracy of critical points of functions related to green functions. Green function. Zhijie Wang already count the number of trivial critical points. They prove that Gn always has trivial critical point, and the number of trivial critical points is at most 2n plus 1. And this 2n plus 1 is optimal. That is for almost all torus, including the rectangular torus, the number of trivial critical points is exactly 2n plus 1. Exactly 2n plus 1. Joined with Lin, we can give a complete answer for tau is purely imaginary. That is, the torus is a rectangular torus. We can prove that as long as the torus is a rectangular torus, then this equation, for any integer n, this equation has no solutions. So then the green function Gn has no non-trivial critical points. So for tau is purely imaginary, Gn has exactly 2n plus 1 critical points, which are all trivial critical points. This result tells us what? Remember, when low is not a pi times n, this equation always has solutions. So for rectangular torus case, this equation has solutions if and only if low is not A pi times n. And this result also give us a difficulty to prove this result, because when you perturb this number, then this equation have solutions. The second difficulty is that if you fix this number but you perturb the torus, then this equation also may have solutions. So these two conditions, purely imaginary and A pi times n, these two conditions are essential. So far we cannot give a PDV proof of this result. We proved this result by showing that the monodromy of the Lamé equation cannot be unitary for any b, and as long as tau is purely imaginary. So we need to apply the connection between this PDE and the Lamé equation. And we prove when tau is purely imaginary, then the monodromy of the Lamé equation cannot be unitary. So since this equation have solution is equivalent to the existence of B such that the Lamé equation has unitary monodromy, so we can obtain the non-existence of solutions for this PDE. So for the case tau is purely imaginary, the previous result already told us the green function Gn has exactly 2n plus 1 critical points, which are on trivial critical point. And later we can say more. We can say all these critical points are non-degenerate. These 2n plus 1 critical points are all non-degenerate. And this result has an interesting application to this mean field equation. So for tau purely imaginary, we already said that when low equal A pi times n, this equation have no solution. But we can say if low is bigger than A pi times n, a small perturbation, then this equation has exactly n plus 1 solution. N plus 1 solution. And for low smaller than A pi times n, also a small perturbation, then this equation has exactly n solution. So we can apply the non-degeneracy and the number of green functions to give the exact number of solutions of this equation. The equation when low is a small perturbation of this critical parameter. So the previous result is about tau is purely imaginary. For general tau, these two questions are still remains largely open. Recently, we can give an answer to the non-degeneracy for generic tau. So we define a set On to be the set of tau such that the Gn has degenerated critical points. Then we can prove that this set is Lebesgue matrix 0. So in other words, for almost all tau, any critical point of Gn is non-degenerate. This result is almost sharp because it was proved by Professor Lin that this set contains at least countably many analytic curves along which this Gn has degenerated trivial critical point. So the novelty of this new theory is to prove that the set of those tau for which Gn has degenerated non-trivial critical point is also of Lebesgue matrix 0. Sorry. I think this is a conjecture. We also think we suspect that for those tau for which the Gn has degenerated non-trivial critical points also consist of countably countably analytic curve, but non-trivial critical point is more difficult to study. So right now we can only say the set is of Lebesgue matrix 0. We don't consider this question. We can consider it later. Yes. So now let me introduce how to connect this PDE with the Lamé equation. So let U be a solution of this equation. Then you consider Z is a complex variable. Then you consider this function UZZ minus 1/2 UZ square. And you take derivative with Z bar, then you see the derivative is 0 using this equation. So this function is a melomorphic function. So and is a double periodic, so is an elliptic function. And use this then you can see this elliptic function has a double pole at 0. So you can see that is this B such that this function can be expressed by this formula. And by this formula, you can see that this function is a solution of this Lamé equation. But this function is real valued and positive. So you can prove that exists a basis of solutions y1, y2, such that this function can be expressed in this way, because this function is positive, real valued and positive. And from here, you can see the monodromy matrix of this y1, y2 are unitary matrix. What I mean, monodromy matrix, for this Lamé equation, although this Lamé, the potential has a singularity at 0, but you can prove that any solution of this Lamé equation is single valued near the singularity 0. That 0 is not a branch point. So any solution is single valued, and then by analytic convention, they are melomorphic in the whole plane. So we have two basic pairs. So if y1, y2 is a basis of solutions, then so is y1z plus a period. So there are two basic monodromy matrices n1 and n2 such that this term can be expressed by y1, y2 with this matrix. So from here you can see why the monodromy matrix is unitary. So you know, because U is a solution of the PDE, so this function is doubly periodic. The left-hand side is doubly periodic. So you have this you have this relation, and you can write this in this way. Because using this. So this relation tells us the matrix satisfies this condition. So Nj are unitary matrix. So that's why if U is a solution of this PDE, then you get a B such that the monodromy matrix of this Lamé equation are all unitary matrix. So this is a connection. So we consider the Lamé equation not necessarily coming from the elite PDE. That is, we consider all B, any B. Then you ask when the monogeomy matrix N1, N2 can be diagonalized. So Zhijie Chen proved that there is a polynomial called Lamé polynomial, degree 2n plus 1, such that if B is not zero of this polynomial, then up to a common conjugation, these two monogeomy matrices can be diagonalized. If B is a zero, then they cannot be diagonalized simultaneously. And then N1 is in this way and N2 in this way. And here, this is a this is a number C. We call this C the monogeomy data. So how, for example, how to prove the non-degeneracy of trivial critical point? Let A be a trivial critical point of the multiple green function. Then we using this A1, AN, we define BA. Then this BA is a zero. We can prove this BA is a zero of the polynomial. So this BA corresponding to a monogeomy data C. So we can prove the Hessian of the GN at this trivial critical point can be expressed in this way. These two terms are non-negative and times the imaginary part of this C. And if BA is a simple zero of this polynomial, then P1 is positive. And P2 equals zero if and only if this C is infinity. If this happens, then this A is degenerate. So the trivial critical point is degenerate if and only if either BA is a multiple zero of the polynomial or the monogeomy data C, that is this one equals zero. So C is real or infinity. And then we can prove that if tau is purely imaginary, then the monogeomy data is purely imaginary and not zero. And if tau is purely imaginary, it is well known that all zeros of the Lamé polynomial are simple. So from here, we, with hope of the monogeomy data from the Lamé equation, we can prove that all trivial critical points are non-degenerate. Now let's turn to the case that N1, N2 can be diagonalized simultaneously. Then N1 can be expressed in this way and N2 in this way. So there are two parameters, R and S. R and S cannot be half integers. Of course, R and S are not unique. So you can define an equivalent relation between RS and R prime S prime if they have this relation. Then the trace of the monogeomy matrix Nj is independent of the choice of solution. So RS is unique under this equivalent relation. And we call this RS the monogeomy data. So we got a map. We got a map from tau B to the monogeomy data R and S. You given a tau and a B such that B is not zero of the Lamé polynomial, then you got monogeomy matrix in this way. So you got RS. So you got a map. You got a map from tau E to R and S. So we find that this map satisfies a surprising universal law. So given any n, this map is holomorphic and locally one-to-one, and it satisfies this universal law. This universal law, first, this is a constant independent of tau and B. And second, this constant is also independent of n. It's also independent of n. So we call this this is a universal law. Is there any geometric expansion of this universal law? We so far we don't find such a geometric explanation. And this universal law has interesting application to the spectrum of the associated Lamé operator. Lamé operator. And the proof of this universal law is very complicated. We need to apply module forms from number theory and the Penn-Weyl equation from the integrable system. So we don't give the details. So finally, I want to say something about the spectrum of the Lamé operator. Lamé operator. When tau is purely imaginary, the spectrum of the Lamé operator in very long time ago, you already know that the spectrum is this form, is a union of finite closed intervals together with this interval, and the endpoint of this interval are all the roots of the Lamé polynomial. That is, we know that the spectrum of the Lamé operator, in general, not necessarily lies on the real axis. That is, in the spectrum may be complex valued, But for tau is purely imaginary. The spectrum is a subset of the R, and consists of finite closed intervals. For general tau, the spectrum no longer lies on R and become very complicated. Here the general result says that for general tau, the spectrum consists of finite bounded simple analytic arcs and one semi-infinity simple analytic arc. And the finite endpoint of such arcs are those zero of the Lamé polynomial with odd order. And for general tau, different arcs might intersect with each other. So for general tau, the picture of the spectrum might be very complicated. So we want to generalize this result to this operator. This operator has a Chebyshev potential. If n1, n2, n3 is 0, then this operator is just the Lamé operator. These are omega 0 is 0, and omega 1, omega 2, omega 3. These are the three half period of the torus. This potential is a generalization of the Lamé potential. And this potential is well known as elliptic solution of stationary KDV hierarchy. So we want to ask, if tau is purely imaginary, whether the spectrum of this operator is also lies on R? This is our question. So it turns out the situation becomes complicated and it is no longer true. So we introduce these two conditions on the parameters nk. So our result is that if n satisfies neither this one or this one, that is, if n if this one does not hold and this one also does not hold, then the spectrum is also in this way, given by this way. But if n satisfies this or this, then the spectrum is no longer a subset of the R, is no longer a subset. It is still symmetric with respect to R, but not contained in R, So the spectrum is no longer in this way, So this is a So this condition, these two conditions is necessary and sufficient. Necessary and sufficient. So I stop here. Thank you very much.